Good morning, everyone. I am Pradeep Gupta, a postdoctoral fellow at Department of Mechanical Engineering, Indian Institute of Science, Bangalore, in collaboration with Anti-Enemy Norway. In this talk, I am going to speak about application of supersonic ejectors in energy conservation devices. So, this would be the contents how I'll do in my presentation. So first I'll explain what is the supersonic ejectors. Then why we'll use supersonic ejectors, what are the benefits of supersonic ejectors. Then we'll see what are the different application of supersonic ejectors. And supersonic ejectors involves the basic knowledge of short waves. So we'll briefly explain about short waves. Then we'll see how the ejector works. Then a few slides on the experimental investigation of ejectors. We'll see how the flow inside the ejector will look like and what are the characteristics of the ejectors flow. Then we'll conclude this with a summary. So this is the schematic of a supersonic ejector. It has four main parts: the primary nozzle, a suction chamber, a constant area suction, and a diffuser suction. Two fluids, the blue color is at low pressure and it's called the secondary fluid, and yellow color is at high pressure and it's called the primary fluid, enters in the ejectors. The primary fluid enters in the ejector through a supersonic ejector, which is the convergent divergent nozzle. So in the convergent part, as area decreases, the primary flow accelerates and reaches to sonic velocity at the nozzle throat. Further expanding the area will result in the increase in the velocity, and it increases to supersonic velocity at nozzle throat. Since the velocity is in supersonic, the pressure in this region will be very low, and that causes the secondary flow to enter in the ejector. Due to the lower secondary flow, the primary flow further expands and it forms a set of short structures. When primary and secondary flow come in contact, it produces the shear layer or the mixing layer, due to which the primary and secondary flow start mixing, and it is expected that the primary and secondary flow mix completely towards the end of the constant area section. Here the primary flow is supersonic and secondary flow would be subsonic or sonic based on the operating condition. The mixture of these two fluid then would be either supersonic or subsonic, based on which ejector operation has been classified as two different regions called the critical flow region and mixed flow region. That will be explained in the further slides. Overall, the work of ejector is that to compress the low pressure fluid by the help of the high pressure fluid to the intermediate fluid. Here the compression effect will be produced without any use of electricity or any hydrogen energy, if you are aware of. That's why it's called the thermal principle of compression, and also it does not consist of any moving parts and hence required less maintenance. Also the geometry of these ejectors are very simple, as we can see only convergent divergent dots. Yeah, as I mentioned that the flow structure inside the supersonic ejectors involves the short interaction. So for few slides I just explain what the short is, or how the short wave generates, and what are the different representation of the short waves. So a short wave is an infinitesimal small region across which there is a sudden change in the stress, density, and temperature. So these are the three representations of short structure. The first one is called normal short. It is also termed called as Stransa because thrust is the flow. There is a significant change in the velocity. So in Tamil, Mach number is more than more than 1. That means the flow velocity upstream is more than the speed of sound, and as it encounters the normal sound, the velocity reduces to subsonic. That means the velocity reduces to less than speed of sound. On the other hand, the pressure, density and temperature increases across the normal sound. The other type of represented Sath structures are oblique Sath and expansion wave, which produces when a supersonic flow meets with the wedge or the tone. So when the wedge wedge has the active tendon, or the flow has to move towards the flow, it produces a compression wave that's called oblique Sath as well. A thrust switch, then the Mach number reduces, pressure, density, temperature, all these properties has to increase. The only difference between the the normal Sath and oblique Sath is that Mach number downstream of the oblique Sath need not necessary to be less than 1, because these are the weak Saths. The third one is the expansion wave, where the flow expands and the Mach number increases, while other property like pressure, temperature, density decreases across the expansion wave. So these are the how the Sath wave generate, or what are the different scenario where we can see the Sath waves. So first one is the blast wave. So I'm not sure whether you can see here very thin line that is called as a Sath wave, which is indicated by this black arrows. The transonic flight. So transonic flight moves with the Mach number of 0.8 to 1.2. So even the Mach number ahead of this flight is 0.8. Once the flow will move over the body, it slightly compresses, which increases Mach number beyond 1, and as a result will have a kind of Sath here. In hypersonic flight, we can clearly see this the eject flow after the nozzle has a series of Sath. In the launch vehicle also, when the below or in the exhaust dash, we can see a series of Sath waves as well. So this is that how the ejector the working principle is. So first the flow comes in the ejector, it becomes the Mach number 1 at the throat, and then it expands to the supersonic velocity. The secondary flow comes in and it gets shot at the virtual throat. Then they started medicine, and the primary and secondary flow medicine ends at the end of the constant area section. Since the velocity is supersonic here, so it expands slightly, and then the normal Sath. The flow becomes subsonic after that, and we have the pressure recovery in the diffuser section. As I mentioned, there are two operating regions. One is the critical flow region and one mixed flow region. So these are the schematic of the different flow region. So we can see this blue line is the secondary flow, and the yellow is the primary flow. Primary flow gets shot in the nozzle throat, that produces supersonic velocity for the primary flow at nozzle exit. Since this nozzle is under-expanded, or the pressure in the secondary flow is lower than the pressure in the primary flow further expands, and it creates a converging passage for the secondary flow, which allows secondary flow to reach the sonic condition, or the secondary flow reaches Mach number 1 at this point. Even we don't have any physical boundary between primary and secondary flow, but the expansion of the primary flow allows secondary flow to choke at this point. And since though no physical boundary involved, we call that as a virtual throat. As we all know, when the flow is short, it allows the maximum mass flow rate. So the primary flow is short and it allows maximum mass flow rate of m dot p, and secondary flow is short and it allows the mass flow rate of m dot s. So That's why the increment ratio, which is defined as the secondary mass flow rate to the primary mass flow rate, is remain constant for the triple flow GCM. On the other hand, if the expansion of the primary flow is not enough to constrain the secondary flow to reach its choking condition, secondary flow flows in the ejector unchoked. And we know if if the flow is unchoked, if we increase the bath pressure, the mass flow rate will decreases. That happens if that happens, the increment ratio decreases with the bath pressure, with the secondary flow is decreasing while primary flow remains constant. So as we mentioned that ejector has simple geometry, it does not have any moving part. So it has application in different areas, and areas are mentioned here like the vapor ejector refrigeration system, transcendental ejector refrigeration system, waste heat recovery, high altitude test facility, high speed wind tunnel testing, thrust argumentation, jet noise suppression, supercritical CO2 power cycle, fuel cell anode reservation, power plant vacuum generation, multi-mode ram scramjet engines, pulse detonation engine. So we can see the ejector application is expanded in the aerospace application, waste heat management, as well as the mechanical systems. In this work, we are more focused toward the energy application of ejector. So the application of ejector in field of or in the domain of energy is mentioned in this diagram. So we can see the ejector has been utilized as waste heat recovery, refrigeration system, fuel cell anode recirculation, power plant vacuum generation, and supercritical CO2 power system in the domain of energy. Now moving towards examples of these different systems where ejector has been employed. So first one is the vapor ejector refrigeration system. This is an alternative refrigeration system to the vapor compression refrigeration system. And I am sure that you know about vapor refrigeration system, where we have the evaporator, throttle valve, the condenser, and the compressor, which requires the mechanical power to drive the compressor. Instead of compressor, we use ejector, a generator, and a small pump in the VERS system, ejector refrigeration system, where we only pump requires the mechanical power, and the worth required for pump is about 5 to 10% of the worth required by the compressor. So using this system, we can reduce the dependency on the electricity for refrigeration or cooling purposes. So in the idea of this system is that we just after the condenser, the liquid part is split in two parts. One sent to the evaporator after throttling, and one other is sent to the generator after pumping it to the high pressure. The high pressure liquid that's heat from the waste source or the solar heat or industrial heat to heat the high pressure CO2, high pressure refrigerant to make the primary fluid, and that's sent to the ejector, which help us to compress the secondary flow coming from the evaporator. In another cycle where the ejector has been utilized as the waste heat recovery, in this system the heat rejected from this VCRS system has been utilized to produce the high pressure vapor for the VERS system, and this system has been explained earlier. So using this system for automobile application, we can increase the fuel efficiency by 45%. The similar way, the third one is that transcendental CO2 refrigeration system. So in these two systems, ejector has been utilized as the compression device, or where we are replacing compressor with the ejector. While in this case, ejector is being used as a throttle, as expansion device, or replacing the expansion valve. In carbon dioxide transcendental refrigeration systems, the pressures are a pressure difference between the gas cooler and evaporator is very high. That results in the huge losses in the throttle valve. So just to improve the efficiency, we are using ejector as an expansion device where the high pressure gas expands to intermediate pressure by mixing with the evaporator fluid, and also the evaporator fluid is slightly pressurized, that requires the less work to the compressor. So after separation, the liquid and vapor part is separated in the separator. The vapor part sent to the compressor, and that reject heat to the ambient in the gas cooler, while the liquid part is sent to the evaporator after expanding in the throttle valve. So in this case, the throttle valve sees a very low pressure ratio. That's why the irreversibility decreases. The other throttle valve here has been used just to control the mass or for the mass balance. This time. The fourth one, ejector, has been used in the power plant. So in this ejector, with the help of the motive stream coming from the high pressure turbine, it sucks the condensable gases from the condenser or any air particle, so it can maintain the lower condenser pressure. Since the pressure decreases in the condenser, the low pressure turbine can expand further, which produces the more worth input, more worth output. So with this, the efficiency of this power system can be improved. In the fifth one, here ejector has been used in the fuel cell stats. Normally fuel cell stat, we are providing the hydrogen in the SS for the complete this one combustion of hydrogen at the anode. So in that case, the unbound hydrogen will be wasted to the ambient. To just reduce the wastage, or to utilize this hydrogen particle at anode, we are using the ejector, which sucks the unburnt or unconsumed hydrogen by the low pressure created from the hydrogen tanks. So this is the experimental setup at Laboratory for Hypersonic and Shortwave Research at the Department of Aerospace Engineering at Indian Institute of Science, Bangalore. So we have the tanks here to store the high pressure air. We have the compressor which produces high pressure airs, and we have the dry cooler to make sure that air those in the pressure vessel will be very dry, so that there should not be any contamination in the this is air receivers. These are trap section where we can see this ejector, the convergent, divergent, and it's very small, but yeah, we can see point out the nozzle inside. The secondary flow coming from this way, and this ejecting from the ejecting to the ambient in this way. So this is the schematic where these are the air receivers we send to the ejector by a primary nozzle, where we can control this pressure regulator. We can control the primary stationary pressure to study the at different operating condition. We have pressure measurement and mass flow rate measurement technique to see the performance of this ejector. In addition, we have the slurring arrangement and the mesh scattering or the PIB arrangement for the flow visualization as well. So this is the laboratory at LHSR. Now with the mass flow rate measurement at different condition, we can see these are the characteristics of the critical flow region, and increasing the compression ratio, the intermittent ratio decreases, which is the characteristics of the mixed flow region. So with this, we can clearly differentiate between the mixed flow region and critical flow region experimentally. Here, these are the pressure profile in mixed flow region and the critical flow region. So the dip in the pressure, this dip in the pressure corresponds to the primary flow expansion in the mid cylinder, while the another dip corresponds to the expansion of the midst supersonic flow in the diffuser, and this steep rise in the pressure corresponds to the soft structures inside the diffuser section. The flow turns subsonic, and the gradual pressure rise corresponds to the subsonic pressure recovery. While in case of midst flow region, the expansion of the primary flow is not that enough, as I explained in the schematic, such that the pressure is deep rising, and once it goes in the diffuser, there is a gradual rise in the pressure due to the pressure recovery. Now we can see the flow structures in the typical flow region and the midst flow region. So we can clearly see that the shot strength in this is very high, because with the turn thrust we can see the strength of the shot in the midst that for the typical flow region is high. That's why we have the low pressure in this one, as well as we can see in this region that one kind of shot is moving, that we terms as a recompression shot structures, and due to that we can see another dip in the dip in pressure for typical flow region, but there were no dip in the pressure for the midst flow region, because there is no shot structure present in the diffuser. So as per summary, ejectors are energy conservation devices that are driven by low grade energy like heat or waste energy. As I mentioned, that ejector does not contain any moving part, so it requires less maintenance. It has wide ranging application in several energy conservation devices along with aerospace and mechanical domain. Augmented ejector with mechanical system improves the overall system performance. Based on aerodynamic choking, ejector operations are classified as double choke and single choke mode. The double choke mode called typical flow region, and single choke mode called the midst flow region. Double choke mode ejector is with better performance and are employed in mechanical system like refrigeration system, power generation, and waste heat recovery. On the other hand, single choke ejectors allow more mixing of the primary and secondary flow. That's why they are found in the aerodynamic systems such as the propulsion system or the rocket-based turbine engines and the fuel cells as well. So these are the references. Thank you everybody for the listening this lecture. Thank you.